bit more algebraic talk, and we're happy to have Sergey Mozgovoy from the Trinity College in Dublin. And so the title is on his first slide, the Invariants and Vertex Algebras. Sergey, please.
Thank you very much. So first of all, thank you very much for the invitation. So this talk will be about DT invariants and also about cohomological Hall algebras and their relationship to vertex algebras. And it is based on a preprint which appeared last year, and it's a joint preprint with Vladimir Dotsenko. So let me talk a little bit about motivation. Cohomological Hall algebras were introduced by Kontsevich and Zoiberman as a mathematical incarnation of the so-called algebras of BPS states in string theory. And their definition is actually quite similar to the definition of usual Hall algebras of abelian categories. But in the case of these usual Hall algebras, one considers spaces of constructible functions, or well, the very first definitions were working actually over categories defined over finite fields, and then one considered all possible functions on the categories, well, on the set of isomorphism classes of objects. While in the case of CoHAs, one uses cohomology groups. So instead of constructible functions, one uses now cohomology groups. And the corollary of this is that sometimes these new Hall algebras are easier to describe. One just needs to find the corresponding cohomology groups and then, well, find the product, of course, and so on. So in general, cohomological Hall algebras can be defined for appropriate three-Calabi-Yau categories, or more precisely, triangulated three-Calabi-Yau, well, abelian triangulated three-Calabi-Yau categories. In particular, if we start with a quiver with potential, then one can associate with such a structure a derived category, which would be a three-Calabi-Yau category. And this derived category is a derived category of differential graded modules over the corresponding Ginzburg differential graded algebra. But in this talk, I will actually consider just quivers with trivial potentials. So potential will be 0. Now, if one considers Poincare series of CoHAs, and I will discuss this notion a little bit later, then one gets an access to the so-called Donaldson-Thomas invariants of the corresponding categories. And what this means is that if we get a better understanding of intrinsic structures on our CoHA, then we can get a better understanding of properties of the corresponding DT invariants. Now, what about these intrinsic structures of CoHA? It was suggested by Kontsevich and Zoiberman that CoHA, I will denote it by H from now on, for a fixed quiver with potential, can be identified with a Hopf algebra. Well, in this case, it is just the universal enveloping algebra of some graded Lie algebra G. And moreover, this graded Lie algebra G, well, one can think about it as the space of a single particle BPS states. So
it's better to say quantum. It's not, or it's sort of a quantized enveloping algebra rather than just universal enveloping algebra.
I think, yeah. But, well, anyway, one could say here that, well, what we would like to see is that our CoHA is a Hopf algebra. Co-commutative, or well, I suppose it can be also not necessarily co-commutative, Hopf algebra. And then we interpret G as its Lie algebra of primitive elements. Of course, well, this is just in the case where we really have the universal enveloping algebra. Now, concerning these bialgebra structures or Hopf algebra structures, in the case of usual whole algebras for quivers. One actually has a bialgebra structure, which is guaranteed by Green's theorem, but this whole algebra structure, well, the coalgebra structure is not co-commutative in general. And probably I should say that in the case of CoHAs, there is some analog of the Green theorem approved by Ben Davison, but in order to equip the corresponding CoHA with a structure of a Hopf algebra, one requires that to localize this algebra. Now, going back to quivers, if our quiver is symmetric, and we consider, as I mentioned before, just the trivial potential, then it was proved by Efimov that we indeed have such an isomorphism. So our whole algebra is isomorphic to the universal enveloping of some Lie algebra. And moreover, this Lie algebra G is abelian, and it is of the form G prime X. So it has an even, well, more restrictive structure. So this result has important implications for Donaldson-Thomas invariants. For example, it proves their positivity because, well, basically Donaldson-Thomas invariants will correspond to the characters of the components of G prime X. Now, in our approach, however, we will not try to represent H as a universal enveloping algebra, but we are doing something slightly different. So we again start with a symmetric quiver. We consider its CoHA. And now our goal will be to equip the dual of this CoHA. So because H was an algebra, this dual will be a coalgebra. And our goal will be to equip this coalgebra with the structure of a so-called vertex bialgebra, which I will define later. So basically, this vertex bialgebra structure will consist of a coalgebra structure, which it already has, and some vertex algebra structure, and these two structures should be compatible with each other. Moreover, the space of primitive elements, so here H dual has a coalgebra structure, therefore one can consider the space of primitive algebra of primitive elements, and we show that this space of primitive elements has a structure of a vertex Lie algebra. I will introduce this notion a little bit later. And like in the Milnor-Moore theorem, then this vertex bialgebra is isomorphic to the universal enveloping, but now universal enveloping vertex algebra of this vertex Lie algebra. So C is a vertex Lie algebra, and then we consider its universal enveloping vertex algebra, and it will be exactly the dual of CoHA. Now, concerning the interpretation of Donaldson-Thomas invariants, this vertex Lie algebra is automatically equipped with a derivation. So there is always a derivation of this vertex Lie algebra, and we prove that this derivation acts freely on C, and then the graded components of the space of generators. So with the space of generators, I mean just this quotient. So the graded components of it will be finite dimensional, and their characters will be exactly the dt invariants of the quiver. So we get a very canonical interpretation of dt invariants in this situation. So, well, now my goal will be to decipher most of the notions that I mentioned here.
Yeah, I'm a bit confused here. So you have some additional structure like vertex bialgebra structure, and you have kind of analog of the Lie algebra, which is this vertex Lie algebra. So then this is parallel to the result of Ben-Davison, where for CoHA itself, you have this BPS algebra and basically dimensions of graded components, additive invariants, which is similar to what you say. So what's kind of...
I mean, it's not quite, I mean, it looks maybe a little bit similar, but well, in the case of, so basically what you have H, so this is a result of Yefimov U G prime X, something like this. Or in the case of quivers with potentials, well, there is a generalization, so one also has certain algebras, this BPS algebra by Ben-Davison and Sven Meinhardt, BPS Lie algebra. Now, in the case of just a symmetric quivers potential, this G prime, well, G prime X will be an abelian algebra. So in the situation I'm interested in this would be just abelian. However, in our case, well, first of all, we consider H prime, H dual, which is isomorphic to the universal enveloping of C. And then, well, our analog of G prime, but you can see that we work in the dual situation. So our analog will be C over DC. Now, this quotient C over DC actually has a Lie algebra structure. This is a Borchert's Lie algebra. Lie algebra, but well, the Lie algebra here on C over DC is non-trivial, while the Lie algebra on G prime was trivial. So
no, I'm not claiming that the dual. I'm just saying that for the purposes of DT theory, you can use G prime. Yeah, and you can use your C. So my question is rather, what's the advantage of this extra structure, which is a vertex structure on the dual side, from the point of view of DT theory? Will be, maybe you will speak about that later. Maybe it's not the right time.
I would say it gives a new approach to Donaldson Thomas invariance, a new interpretation of the invariance.
Yeah. Okay. All right.
Well, and I mean, the structure is, I would say, richer because, well, here you have a non-trivial bracket at least.
Yeah, but if you use this richer structure, this is fine. But if you don't, so that's the point. Yeah. So, but okay. Anyway, okay. Yeah. Thank you. Yeah. Mm-hmm.
Okay, so let me go through the definitions of the notions that I mentioned earlier. So first of all, we would like to define cohomological Hall algebras of a cohomological Hall algebra of a quiver. So we start here with a symmetric quiver Q, with a symmetric quiver Q, and we denote by I the set of its vertices. Then we define, as usual, the Euler form on the lattice L equals z to the power I, and we consider the vector space of representation. So I will denote it by Rd. Here D is any dimension vector, and this space parameterizes representations of Q having dimension vector D. So for any arrow A from I to G, we will have a linear map from C to Di to C to Dj. Now, of course, it can happen that there are isomorphic representations in this space. So there is the natural action of the group GD, which is just the product of all GLDI on this space. And well, it is defined by conjugation. And then the orbits are exactly the isomorphism classes of representations having given dimension vector. And then we define the corresponding cohomological Hall algebra H as follows. So it will be an L-graded object in the category of, well, in the derived category of vector spaces, which we will identify with Z-graded vector spaces. So H is a direct sum over all dimension vectors of components HD, and then HD is defined as equivariant Borel-Moore homology of this space RD up to certain shift. And because everything is smooth here, we can use Poincare duality, and we can write that it is isomorphic to just usual equivariant cohomologies up to some shift. So this is a underlying object that we are interested in, but we want, of course, to define a product on it. So in order to define a product, we consider two vectors, D and E, and inside R with index D plus E, we consider a subspace that consists of representations that preserve this subspace inside the larger one. So basically here, this space RDI will parameterize exact sequences M, X, N, where M has dimension vector D and N has dimension vector E. Okay, now there is an action of the subgroup, this parabolic subgroup GDE, which is a subgroup of GD plus E that again preserves this subspace. So there is an action of this group on RDE, again just by conjugation, and then we can consider the corresponding stacks. So first we consider here the stack RDE moduli, and we can map it into directions. So first we can embed RDE to RD plus E, we can embed GDE to GD plus E, so we get this this map. Or having an element in RDE, we can forget all the subspaces corresponding to the vector, to the dimension vector E, and get something inside this stack. Or we can forget everything corresponding to the dimension vector D and get something in this stack. So we have these maps in two directions, and then we use them in to define the product. So what we do is we consider Borel-Moore homology of this stack, which is just the equivariant Borel-Moore homology of RD. We consider Borel-Moore homology of this stack, which is this one. Then we apply the pull back Q upper star, and we land in Borel-Moore homology of this stack up to certain shift. And then we apply the push forward P lower star, and we get something in Borel-Moore homology of this stack. So we get something in here. And so this gives us a map from the tensor product here to this Borel-Moore homologies. And therefore, we obtain the required composition map, the product, from HD tensor HE to HD plus E. And it was proved by Kontsevich and Zedman that this product is associative. But, well, everything here works, of course, in greater generality than just representations of symmetric quivers. But in the case of symmetric quivers, one has a very explicit description of the corresponding CoHA. So this is a result of Kontsevich and Zedman also. And this is a so-called shuffle algebra description of the CoHA. So first of all, let us define the algebra of symmetric polynomials, lambda n, for rational numbers, where we will always consider xe to have degree 2. And then similarly, given any dimension vector d, we define the group sigma d to be the product of the corresponding symmetric groups. And then we define the algebra lambda d to be the tensor product of the algebras of symmetric polynomials lambda di. Or another way to define it is to consider variables x, I, k, where I are elements, well, I is any vertex and k goes through 1 to di, and then take the sub-algebra of sigma d invariant elements. So this will be our lambda d. So it has a very explicit description, and one knows that the equivariant cohomologies of a point with respect to GLN are isomorphic to lambda n, and then similarly equivariant cohomologies of a point with respect to GD is isomorphic to lambda d as a graded algebra. And therefore, the component HD of our CoHA, which is by definition this vector space, can be interpreted as this algebra of, or tensor product of algebras of symmetric polynomials up to certain shift. So again, we have a very explicit description of every component of our CoHA. And now one needs to interpret also the product in the CoHA. So it was proved by Kontsevich and Zoidman that this product, which is a map from HD tensor HE to HD plus E, is given by the so-called shuffle product. So here we start with F, which is an element in HD, or we could say a symmetric polynomial. We start with G, which is another polynomial, and then the product, the shuffle product, is defined as a sum over all shuffles. I will explain it in a second. And then we take, well, we apply this shuffle sigma to the product F of F, G, and K, where K is certain new polynomial, or rather a rational function, which I will describe explicitly in the next slide. So here the sum runs over all DE shuffles, and this means that we consider all permutations sigma in sigma plus in sigma of D plus E, such that, well, we require that at every vertex I, sigma I1 is less than sigma I2 and so on up to sigma I DI, and similarly sigma I DI plus 1 is less than and so on sigma I DI plus EI. So another way to think about these shuffles is to consider sigma D plus E modulo the action of sigma D times sigma E. So basically shuffles give just the representatives of this quotient. Okay, now, well, here in this formula we have the product of F, G, and K, so we need to define this kernel of this shuffle product K. So let us do this in the next slide. So this is a formula that we had before, and the shuffle, well, the kernel that we use here is given by this very explicit formula. So as you can see, so here these powers chi of ij, this well, here chi is the Euler form, and so this kernel is actually a rational function, but it turns out that after this symmetrization, the shuffle product will be always a polynomial if F and G were polynomials. Okay, so this is how one describes the product in the whole algebra. Now, from this very explicit description of the product, one can immediately see that our algebra satisfies the property that G times F is equal to F times G up to some sign. So this property can be formulated in the form that, well, our algebra is actually a commutative algebra if we appropriately interpret this sign. So in order to get an actual commutative algebra, we need to interpret our whole algebra H as an algebra in the symmetric monoidal category. So this symmetric monoidal category is a category of L-graded object in vect Z. And for a symmetric monoidal category, well, of course, we need a monoidal category structure, so we need a tensor product, but this is the usual tensor product. And we also need this symmetric structure, so we need a braiding. which means that we need to be able, well, we need an isomorphism from V tensor W to W tensor V. Now, if V is concentrated in degree D and W is concentrated in degree E, then this braiding is defined using this formula. So we map A tensor B to B tensor A up to this sign. So this sign is responsible for the statements that I made before, that H can be interpreted as a commutative algebra. But again, it is a commutative algebra in this symmetric monoidal category. And from now on, we will always consider just this braiding on vector z to the power L. And so we always consider this symmetric monoidal category structure. Okay, so this is the first part. Well, this is the first part of the story. So this is the description of the CoHA. Now we would like to go to the next side, namely we would like to go to vertex algebras, vertex Lie algebras, and vertex bialgebras. So first, let me remind you briefly the notion of a graded vertex algebra. So this notion of a graded vertex algebra, it will take place in this symmetric monoidal category that I defined in the previous slide. So as before, we assume that we have a lattice L equals z to the power I, and we assume that it is equipped with a symmetric bilinear form given by the Euler form. So because we assumed earlier that Q was a symmetric quiver, the corresponding Euler form will be also symmetric. And then we consider the symmetric monoidal category, which I will from now on denote by C, the category of L-graded vector spaces, with the braiding defined earlier. And we can also equip this symmetric monoidal category with internal Hom spaces. So this internal Hom space will be again an object in C, and it is defined as a direct sum over all D in L, and then we consider components Hom D from V to W. So this describes homomorphisms from V to W of degree D, and it is defined in the usual way using this formula. Moreover, while previously in the case of CoHAs, we worked with cohomological degrees, which were degrees in Z. Now for the language of, well, it's traditional to use for vertex algebras weight degrees. So our weight degrees will be half integers, n in 1/2 of z, and they should be identified with the cohomological degrees equal to -2n, which will be now integers. So whenever we work with, well, sometimes I will talk about weights and sometimes about cohomological degrees, and the correspondence is given by these formulas. Okay, now concerning graded vertex algebras. Well, as usual, one defines a vertex algebra to be a triple Vy1, but usually one works with a vector space or a supervector space, while in our case, this V will be an object in C to the power 1/2 Z. So what it means is that we consider 1/2 Z graded objects in C. We also assume that this object is bounded below, meaning that Vn is 0 for n very small. Then we consider this element called vacuum, which is an element in degree 0 component of V. And finally, Y is a map that goes from V to the so-called space of fields F of V, and it is defined as follows. So here we consider the internal endomorphism space of V, so it will be a graded object. And then we consider power series in Z plus -1, where we equip Z with the L degree equal to 0 and with a weight degree equal to 1. So this new object is actually an object in this category C2 1/2 Z. And well, then we have the usual axioms of a Lie algebra, sorry, of a vertex algebra. So first of all,
except of the typo in 3.5. You
Sorry?
have a typo in 3.5. One of these should be double.
oh yes, thank you. Right. Now here I should mention also that, well, in this last locality axiom, this bracket is not, well, it is a commutator, of course, but it is a commutator in this symmetric monoidal category. So the braid, well, we use a braiding sign when we define the commutator in here. And also probably I should mention this axiom 3.4. So here we define, so just from this triple, we can define the following endomorphism of V, denoted by D, where we map an element A in V to A minus 2 applied to the vacuum. And then the axiom is that we have this equality. And well, as usual, we use notations that y of az is equal to an times z to the power minus n minus 1. Now, because we assumed earlier that the weight of z is minus 1, if we want y to preserve degrees, it means that this element should have the same degree as a, and it means that, well, z to the power minus n minus 1 has degree n plus 1, so we require this equation that relates the weight of an and the weight of a. Okay, so this is a notion of a graded vertex algebra, and now let us define the graded vertex Lie algebras. So basically, a vertex Lie algebra carries just half of the structure of a vertex algebra. So basically, if I will go back for a second, here, in order to define this map Y, we needed operators an, which were endomorphisms of V. And we needed these operators an for all integers n. Now in the case of vertex Lie algebras, we will consider these operators an only for n greater or equal than 0. Moreover, we will also remember the differential that I mentioned earlier, so it is given by this kind of formula. Okay, so let me formally describe now graded vertex Lie algebras. So as in the case of vertex algebras, we need an object. I will denote it by C because, well, sometimes these vertex Lie algebras are also called Lie conformal algebras. So C is used because one calls it also a conformal algebra. Okay, so C will be an object of C to 1/2 Z as before, and then it is equipped with certain maps. So first we have this map D from C to C in the same way as we had it for vertex algebras. We require this map to have L degree 0 and weight 1, and this was also the case for vertex algebras. And then we also consider maps that go from C tensor C to C, but only for n greater or equal than 0. So if we want to compare it with the previous notation, basically, previously, if we would consider a tensor product AD, then we had this linear operators an, and we can apply it to the element B. So this is how these operations were defined in the previous slide. But as I said already, for vertex Lie algebras, we consider these operations only for n greater or equal than 0. And then we list all the required axioms. So as in the case of vertex Lie algebras, one requires that an b is 0 whenever n is very large, and this is actually automatic if, like in the previous slide, we assume that c is bounded below. Then one requires that d is a derivation with respect to operations n, and this axiom was actually also satisfied for vertex algebras. And one also requires this axiom, which is also satisfied for vertex algebras. And then two more technical axioms. This one is called the Jacobi identity, and this one is called, I suppose, commutator identity or anti-commutator. I forgot if it is commutator or anti-commutator identity. And notice that here in this axiom, we have this special sign that, well, it comes from the bilinear form on our lattice. Okay, now
so the
it may look.
The Jacobi identity in 2.4, Jacobi identity in 2.4, that's only for non-negative m and n's, right?
Yes, everything here, yes, everything here is just for non-negative.
Yeah, 2.5 will be needed.
Sorry?
Yes, 2.5 would be needed.
Yes. Yeah, I suppose for vertex algebras, one requires just the Jacobi identity. Everything else will automatically follow. But yeah, here we really require all of these axioms. Okay, now whenever we have such a vertex Lie algebra, one can equip C modulo DC with a Lie bracket. Sometimes it's called the Borchertz Lie bracket. Usually it's used just in the case where C is a vertex algebra. So you consider vertex algebra V and you take the modulo DC and you equip it with that I wrote here. But everything works also for vertex Lie algebras. So the bracket is defined just by the 0 operation. Okay, now something similar can be done with, for the so-called affinization. So whenever we have a vertex Lie algebra, as I described earlier, we can equip C tilde, which is Ct plus minus 1, again with a vertex Lie algebra structure. I will not write down the formula, but everything can be done here. So we can equip it with a vertex Lie algebra structure, and then we can, well, using point 3, we can equip now C tilde modulo D C tilde with a Lie bracket. And this is what I'm going to do. So basically, one defines the so-called algebra of coefficients, which I will denote by L, which is the algebra of coefficients of C, to be the quotient of this C tilde, which is the affinization of C, by the following, by the subspace spanned by the following relation. So let me first introduce notation. I will denote by C of n, C times Tn, so it will be one of the summands here. And for any element A in C and any n greater or equal 0, I will denote by, no, actually n is integer. So I will denote by an, A times T to the power n. And then using this notation, we introduce certain relations on C tilde. Namely, we require that dA of n should be equal to minus n an minus 1. So we sort of explicitly introduce this relation. So yeah, so let me just repeat. We take this C tilde, and then we take the quotient by the subspace generated by all such expressions. Then this quotient L has a Lie bracket, and this is an explicit formula. So this is a Borchert's formula for the Lie bracket on this algebra of coefficients. Again, it may look quite technical, and of course it is, but well, everything works out. Okay. Now, yeah, probably before I will go further, I should mention what is the meaning of this algebra of coefficients. Well, basically the idea is that whenever we have our vertex Lie algebra, there is a map from C to this CL power series Z plus minus 1, where we map any element A in C to the power series AN Z minus N minus 1. And well, there is a structure. There are n operation. Well, operations n operations for n greater or equal 0 on this side, and this map will then preserve such. Will preserve n operations. So there are n operations on C, and there are n operations on this side, and the map that I defined will preserve all of these operations. So, well, this is why one actually defines this algebra of coefficients. Now, the algebra of coefficients has actually a decomposition. So one can define certain sub-algebras, L plus and L minus, such that L is equal to the direct sum as a vector space. So here, these sub-algebras, L plus and minus, are defined as follows. So first of all, recall that because of our definition of the algebra of coefficients, we have this equation in L, which means that we, well, for example, if n is greater than 0, it means that we can express a n minus 1 in terms of dan. And this implies that L0 is contained in L1 and so on. And then we can define L plus to be, well, either the sum or the union of all such components Ln. So this is the definition of L plus. And similarly, one has this inclusion. So L minus 1 contains L minus 2 and so on. And we define L minus to be again the largest one. And then, as I said, we have this decomposition, and moreover, L plus and L minus are the sub-algebras. And yeah, I didn't mention it, but Ln is just the image of Cn inside L. Okay. So this is a useful decomposition. Moreover, it turns out that as a vector space.
Could you tell me Ln corresponds to Z to the L's nth power or Z to the n minus 1 minus 1?
Sorry?
Ln should be L tensor with the Z to the nth power, or there is the L bracket n. What's it?
Oh, this one.
That's right.
Or
is that your definition?
Yes, this is my definition. So it is the well. So here. Recall that C tilde was C t plus minus 1, and Cn was one of the components. So
okay,
Ct
okay.
to the
So
power n.
that has nothing to do with the Z you used on the top. Thank you.
Yes, yes. Yeah, I mean, here we use T just as a device to, well.
That's fine. Thank you.
Okay, now it turns out that actually as a vector space, the vertex Lie algebra C is isomorphic to the negative Lie algebra L minus, which is L minus 1. And well, the map goes, well, in a simple way. So an element A here is mapped to the element A minus 1 in this component. So one can prove that it is always an isomorphism. Now, our next goal will be to define the universal enveloping vertex algebra, which and the construction will be quite similar to the definition of a universal enveloping algebra of a Lie algebra. So first we consider the Fermat module. So we take the universal enveloping of L, tensor over U L plus 1, U of L plus with Q, where we require L plus to act trivially on the one-dimensional vector space Q. And of course, because of this vector space decomposition, we can identify this tensor product with U of L minus. So this will be our Fermat module. And then it was proved in papers by Brink, Katz, and Treutmann that around 2000, that there is a canonical vertex algebra structure now on this Fermat module. And in particular, y of AZ, where A is an element in C, is given by, well, just by this expression. So here AN will be an element, well, it is considered as an element of okay. So this new structure, the structure of a vertex algebra on the Fermat module, is called the universal enveloping vertex algebra of C. And note that as a vector space, U of C, this universal enveloping vertex algebra, is equal to the universal enveloping algebra of the Lie algebra L minus. Of course, it has some universal properties similar to the universal properties of universal enveloping algebras of Lie algebras. And it turns out that such universal enveloping vertex algebras, U of C, have an additional structure, the so-called vertex or co-commutative vertex bialgebra structure. And so in the next slide, I'm going to define this notion of a vertex bialgebra. So first of all, whenever we have two vertex algebras, we can equip their tensor product with a vertex algebra structure, where the vacuum is defined as vacuum tensor vacuum, and Y applied to V tensor W, where V is in the first space and W is in the second one, is defined as this tensor product. So this is again a vertex algebra. And then we define a vertex bialgebra to be a structure that, well, it consists of several components. So basically, we require it to be a vertex algebra, and we also require it to be a coalgebra. So here, delta is a co-multiplication on V, and epsilon is a co-unit, and we require that the structures, the co-multiplication, is a morphism of vertex algebra, of vertex algebras, from this vertex algebra to this vertex algebra, and similarly the co-unit is a morphism of vertex algebras, where this one has a canonical vertex algebra structure. And well, as I mentioned in the previous slide, whenever we have a vertex Lie algebra, C, and we consider its universal enveloping algebra, it has a natural co-commutative similar to the usual universal enveloping algebras of Lie algebras. So it has a co-commutative. Of course, it has a co-commutative coalgebra structure because this is just a universal enveloping, and it was proved by Haish and Lee that this coalgebra structure is indeed compatible with a vertex algebra structure that I defined in the previous slide. So this object has, on the one hand, vertex algebra structure, on the other hand, it has a coalgebra structure from this interpretation, and it was proved by Haish and Lee that these structures are compatible, and therefore they define a vertex bialgebra structure. Now, it turns out that one can go another way around. Namely, if we start with a vertex bialgebra structure, so V is a vertex bialgebra, then we can consider the space of primitive elements. So this can be done for any coalgebra. So the space of primitive elements consists of all x in V such that delta x is equal to this expression. And one proves that this space is automatically a vertex Lie algebra. So it inherits the vertex Lie algebra structure from V. And this is a rather recent result by Han, Lee, and Xiao. Well, this result is actually not particularly difficult. What is more interesting is that if V is a co-commutative connected, and connected here means that there exists exactly one group-like element. So if V is a vertex bialgebra, which is co-commutative and connected, then, we can consider here its primitive elements. So we get a vertex Lie algebra structure. And then we can consider the corresponding universal enveloping vertex algebra. And it turns out that they are isomorphic as vertex bialgebras. So this is a non-trivial result proved in the same paper. And one could consider it as an analog of the Milnor-Moore theorem for Hopf algebras. So in the case of Hopf algebras, one also has, one starts with a connected co-commutative algebra and one proves a statement like this. Okay, I suppose I should be a little bit faster. Okay, now, as I explained in the very beginning, we want to equip the cohomological Hall algebra, or more precisely its dual, with a vertex bialgebra structure. And this vertex bialgebra structure will be a special vertex bialgebra structure called a free vertex algebra. So I will explain now the notion of a free vertex algebra. So basically, we start with a set I, and this I will correspond to the set of vertices of our quiver. And we start with a symmetric map called locality, and that goes from I times I to integers. And we also fix certain degrees in L in our lattice, and degrees, and weights. And then we consider the category of vertex algebras, as I defined earlier, graded vertex algebras that are equipped with maps S from this set I to V. So basically what we want is we want elements in I to generate our vertex Lie algebra. So we require that the images of this map S generate V as a vertex algebra. Then we want elements Si to have prescribed degrees. And finally, the most important property is that we want to fix locality orders of the corresponding fields. So we require that Y of Si and Y of Sj are local of this order Nij. And then it was proved by Reutemann that in this category of all such structures, there exists the initial object, and it is called the free vertex algebra of locality M. Now, it turns out that such a free vertex algebra is actually always a vertex bialgebra, at least if M is non-negative. So I'm going to explain this now. So let us assume that n is greater or equal than 0. So nij is greater or equal than 0 for all I and j. Then we have a very explicit construction of this free vertex algebra. Namely, we consider the set of generators x consisting of symbols in, where I is in I capital and n is an integer. Then we consider a subset that consists of in with n greater or equal than 0. We define certain degrees, L degrees and weights, and then we can identify, well, we can interpret Qx as an object in this required category of L-graded objects, or of Z times L-graded vector spaces. Then, well, basically, we would like to have the locality order of this field I of Z, well, between I of Z and J of Z, to be given by this number Nij. And this locality condition can be written using this formula. So the idea is that we explicitly require that this equation is satisfied. So we define the algebra B to be the quotient of the tensor algebra generated by this object by this locality relations. Then this algebra B is equipped with a derivation. So one can define this derivation also on this tensor algebra, where we map in to minus, well, to this expression. And one can prove that the left B module, B by Bx plus, has this, it is a required free vertex algebra. So it has a vertex algebra structure with the vacuum given by the class of 1 of identity in B, and with fields y of iz given by iz. I'm not sure. Yeah, I defined it earlier. So this will be our yiz. So one can equip the quotient with a structure, with a vertex algebra structure, and it will be exactly the required free vertex algebra. Now, as I said, this free vertex algebra is actually the enveloping vertex algebra of some vertex Lie algebra. Well, in order to see this, we define the Lie algebra L to be, well, just the Lie algebra. So previously we considered an associative algebra, and now we consider the Lie algebra generated by X, subject to the locality relations that I formulated in the previous slide. And then we define its sub-algebra L plus to be the sub-algebra generated by in, where n is greater or equal than 0. So this was the set X plus. Then the algebra B from the previous slide can be interpreted as a universal enveloping of L, of this algebra L. And similarly, the vertex algebra P from the previous slide, which was defined as B by Bx plus, can be interpreted as UL tensor with Q over UL plus. Now, these fields IZ, they can be interpreted as elements in here, and therefore these elements act on P And now, in order to define the required vertex Lie algebra, well, we basically construct this vertex Lie algebra C as a vertex Lie, well, as a vertex Lie sub-algebra of this object by applying non-negative products. So there are non-negative products on this object, and by applying the derivation to the vacuum. So this dz will be also defined on this object. So there is a rather complicated, but still there exists such a construction of this vertex Lie algebra, and it turns out that the universal enveloping algebra of it is exactly the free vertex algebra P from the previous slide. And yeah, probably I should also mention that previously I defined the algebra of coefficients of any vertex Lie algebra, and it turns out that here the algebra of coefficients will be exactly this L that was used in the construction of C. Okay, so seems like I'm a little bit out of time. Yeah, so the idea is that, well, there is another interpretation of the vertex, of the free vertex algebra that I defined earlier, namely, it can be interpreted as a sub-algebra of the lattice vertex algebra. So here we start with a vertex, so with a lattice L. We assume that it is equipped with a symmetric bilinear form. Then we construct an explicit locality function, namely we define Nij to be minus the symmetric bilinear form of the basis vectors Ei and Ej. And then one can, using the previous slides, define the corresponding free vertex algebra, and this free vertex algebra can be actually embedded into the lattice vertex algebra VL. Now this vertex lattice vertex algebra, well, this is a standard construction. One starts with a Heisenberg Lie algebra corresponding to the lattice. Then one considers the corresponding Fock spaces, which are modules over the Heisenberg Lie algebras. And then one defines the total Fock space, which is the direct sum over all D in L of these Fock spaces Vd, and then one can define the structure of a vertex algebra on this VL. So let me probably skip some details. So basically, the structure of a vertex Lie algebra on VL uses vertex operators here, and these vertex operators satisfy this locality relation. So whenever we have vectors D and E, and we consider the corresponding vertex operators, one knows the locality order. It's given by the bilinear form. So in particular for our locality Nij, which is given by this expression, we know what will be the locality between the corresponding gamma Ei of Z and gamma Ej of Z. And this formula tells us that the locality between these two operators will be exactly the locality Nij given by this formula. So it tells us that there exists, by universal properties, there exists a map from this free vertex algebra to the lattice vertex algebra, and it turns out also to be an embedding. So this is another interpretation of a free vertex algebra situation. Okay, and now finally, let me go through the relationship between, well, on the one hand, cohomological Hall algebras, and on the other hand, those vertex bialgebras that I just defined. So as before, we have a symmetric quiver Q. We consider its set of vertices I, the corresponding Euler form, the corresponding lattice. Then H is our CoHA, P is our free vertex algebra for this particular locality. Then we have a decomposition of P into components, where this P with index D is generated by the following expressions. So probably I need to apply it to the vacuum. So whenever we have such an expression, we say that its weight is equal to this vector inside L, and we define its, this is the L degree of this expression, and this will be its weight. So anyway, P has a decomposition, and L decomposition, and using it we can define the dual of P component-wise, and then is that we have an isomorphism between PD dual and the component of the whole of the cohomological Hall algebra, which, as I explained earlier, can be identified with symmetric polynomials up to a shift. And well, the map goes as follows. Whenever we start with some psi in this PD dual, we consider here the matrix coefficient. So here we apply so we express D as this sum, so for some sequence of vertices I1 up to IP, and then we consider, we apply those fields to the vacuum, and then take the pairing with psi. So this will be a certain expression, and it turns, well, because of locality, if we multiply this expression with this product, everything here will be a symmetric polynomial. So it will be actually an element in lambda D. So this is how one constructs this map between the dual of the free vertex algebra and the CoHA. So, well, this is of course here just an isomorphism between vector spaces, but we prove that this isomorphism actually induces the isomorphism between coproducts. So, well, if we dualize this isomorphism, then it will be an isomorphism between P and H dual. So H dual has a coproduct, and it is explicitly described using using the shuffle product on H. And on the other hand, we know that P is the universal enveloping algebra of some vertex Lie algebra C, and therefore it can be written as a universal enveloping algebra of a Lie algebra. So it automatically has a coproduct. So we prove that the coproducts are preserved under this isomorphism. And a couple of words about relation to DT invariants. So basically, yeah, probably I need to be really sketchy here. So whenever we have an object in here, so it's L times Z graded object, as for example the cohomological Hall algebra, we can define its Poincare polynomial, where we just compute the corresponding dimensions and yeah, we write this expression with certain signs. Now,
Polynomial, it's a series.
oh, it's a Poincare series. Yes, thank you. Now, because we have a very explicit description of H using symmetric polynomials, we can easily write down the corresponding Poincare series for the cohomological Hall algebra. So here it is. Now, because of our isomorphism, H hat isomorphic to P, this gives us also the Poincare series of this vertex Lie algebra. So this will give us, so the previous result gives us also the Poincare series of this free vertex algebra, and this was actually a result proved earlier by Milosh and Penn. So about the character of this free vertex algebra. Now, concerning the relationship to Donaldson-Thomas invariants, these invariants are defined using the so-called exponential. So on the left-hand side, we have Poincare series of the CoHA, and then those invariants appearing here are called Donaldson-Thomas invariants. Now, in our case, we proved that H, or more precisely here, H dual is isomorphic to P, and therefore it is isomorphic to the universal enveloping algebra. And this implies that Z of H dual can be written as the Platistic exponential of Z of C. So this provides us a relationship between the Poincare polynomial of C and Donaldson-Thomas invariants. And moreover, we show that Donaldson-Thomas invariants themselves are given by the following formula. So this is the Donaldson-Thomas invariant, and it is equal to the characteristic polynomial, or sorry, to the character of C modulo DC. So probably let me write it here, which is character of C modulo DC, where recall that C was a vertex Lie algebra, and therefore it automatically has a derivation. So everything here, well, it has a canonical structure. So in particular, it gives us a new proof of non-negativity of Donaldson-Thomas invariants. So I suppose, unfortunately, that, well, I already spent more time than I should have. So let me probably stop here. Thank you.
Yeah, thank you. Yeah, it's sort of a bit formal because I still do not understand why this vertex algebra, why it's relevant. I mean, you can, well, first, of course, there was this proof of Yefimov of integrality, which actually also was a bit formal because Yefimov did not describe explicitly this PPS Lie algebra, but I believe after Ben Davison we can kind of do it quite, I would say, geometrically. So then,
Jan, I suppose actually the proof of Ben Davison, well, it relies, I suppose, on some previous paper by Sven Meinhardt and Ben, and this paper in itself relies on the paper of Sven Meinhardt and Markus Reinecke, and this paper actually relies on the paper of Yefimov. So it's a complicated relationship, but the result of Ben depends on the result of Yefimov.
It does not. I mean, the proof depends, but not the result. It's actually
yes,
the fact that this refined BPS invariants, as physicists would call them, or motivic Donaldson-Thomas invariants, as we call it with Maxim. So, I mean, they are expected to satisfy this integrality property, all right? So then Ben gave, probably with Meinhardt, they gave an explanation which was expected by us with Maxim, that there is some underlying graded Lie algebra, and so these invariants are, roughly speaking, Poincare polynomials of this vector space as a graded vector space, something like that. So it's all expected, and as you know, by analogy with Katz's polynomial, it's not very surprising. So my question is about the role of this vertex algebra structure. That's what kind of mysterious, because CoHA is indeed related to vertex algebras, and not only in the case of symmetric quivers, which is kind of 2-color bial, but in the case of 3-color bial. So these are more complicated vertex algebras. As far as I understand, you see no more than Joyce sees, namely lattice algebras, lattice vertex algebras, and this is it. But there are more complicated, which kind of have really, they appear in nature. Unfortunately, Tomas Prochaska, he left early because probably it was too dry for him, but he could confirm that indeed there are interesting vertex algebras and their generalizations. So I would like to understand what's the reason, not because you can prove something, it does not explain why they appear. You see, sometimes.
Okay, I mean, maybe I could switch also to this slide. This is what you, I suppose, just mentioned, the structure of Joyce. Now, well, the Lie algebra structure of Joyce on certain moduli spaces.
Yes, yes. And in your case, it's R-home or something, I believe. Yeah, it's in your, exactly. It's in your part 4. That you have a stack of objects of some category, yeah, and in this stack you have, well, perfect complex or whatever, perfect sheaf something with theta, which in your case it's R-home, and I believe in Joyce examples it's more or less also R-home, but
well, it's a symmetrized R-home or something like that.
Yeah, symmetrized. All right. And so then you can construct in a pretty formal way some vertex algebra, and well, which is essentially based on the cohomology of your stack and some additional complex on the square, and this is it. And I don't know whether there is any non-trivial mean besides of lattice algebras and their relatives, any non-trivial vertex algebra which can be obtained in this way.
Yeah, okay, I will honest, I also don't know. I suppose, I mean, they tried to use this technique, but so far unsuccessfully to consider, for example, the case of quivers with potential, but
there are,
well, something doesn't work here.
That for the, yeah, so that's a problem, because you should certainly somehow, in the case of 3-dimensional Calabi-Yau, you should consider not this symmetrized X as theta, but something more complicated, which depends on the Calabi-Yau potential of your category. And there are answers. In particular, there is this big work by Yamazaki, Galachov, I forgot who was the third, but I invited Galachov, will give a talk later in February on that story. And it's called, they call it quiver Youngians. And we had the paper with, with Rabchak and Yapin.
Yes, but I suppose this is a very particular story for this is just for quivers arising from brane tilings. So this is only for very special quivers with potentials.
Yes, I agree, but yeah, absolutely, you are right. But the point is that it's more general than symmetric quivers.
Well, it's a non-trivial quiver, I would say. Yeah, non-trivial
And
potential.
the non-trivial potential, well, you cannot reduce it just to a single Tucalabiao. It's like three-dimensional partition. You can slice in three different ways to get a two-dimensional partition, which correspond to the Hilbert scheme of C squared. And three-dimensional partition is a Hilbert scheme of C cube. So then if you have a toric Calabi-Yau, like brane tiling, toric diagram, with some multiplicities, then indeed you can construct some vertex algebras, but they are non-trivial, which means that they cannot be obtained, at least literally, by Joyce construction or by your construction. But nevertheless, they are related to CoHA. And the way we obtained it, we used CoHA. Yamazaki maybe didn't use CoHA, but he was very well aware. Yeah, so there is some conceptual reason why CoHA is kind of gives rise to vertex algebras. And so that's kind of, it was not clear for me before you talk, and it is still.
Well, it's not about this topic for sure. Yes, so I don't know. I don't know how vertex algebras appear in that story of yours with Rabchak et al. And of Yamazaki.
It's more than our paper with Rabchak. It's more than Yamazaki. You see, on CoHA, there is a structure of factorization algebra, and somehow it is reflected in the formula, in this shuffle algebra formulas, which you reproduced at the very beginning. But anyway, it's something about collection of points which you can group together. There was this paper by Kapranov and Vassero about CoHA for surfaces, and they have, I think, a section in their paper, CoHA as a factorization algebra. And factorization algebras, they are kind of, it's a very general structure, at least according to Castello. They appear basically in any quantum field theory somehow. So then, and they play the same role as VOA. Basically, you consider your kind of abstract axioms, which you kind of, for people who never saw them before, it's impossible to understand these axioms of vertex algebras. But morally, you consider quantum field theory, like conformal field theory, with a space-time which is a curve, and you place kind of operators at the points, it's vertex operators, and then you look for the operator product expansion, which satisfy this locality property. Great. So this is a very special case of a quantum field theory. And factorization algebras, it's more than that. It's something which appears in four-dimensional quantum field theories and so on, so on. So then maybe, I don't know, probably mathematicians, neither mathematicians nor physicists are not ready kind of to study carefully how to derive CoHA from kind of more general in more general setup, like for any, in the setup of, for example, of Costello's book. Yeah. And to derive sort of a vertex algebra structure, whatever is it, maybe it's more complicated than what than these Borchardt axioms. Maybe it's more difficult in higher dimensions, but nevertheless, there is some kind of a chiral algebra, which probably can be derived from this CoHA, from factorization algebra in maybe in a formal way, but it's straightforward way. And so all these probably would be just examples. But the reason is this strange factorization property. Like when you compute cohomology of the moduli stacks of representations of a quiver, so by torus localization, you can reduce it to the cohomology of these stacks with respect to the maximal tori of the product of GLNs. And therefore, they are modules over the, just by general reasons, yeah. Equivariant cohomology of anything are modules of equivariant cohomology of the point. Equivariant cohomology of the point with respect to the torus, it's just sort of polynomials, yeah. So basically, you speak about coherent sheaves on some spaces, and these in this shuffle algebras, these factors, they correspond to certain subspaces. And so you can consider points which kind of collide, belong to this subspace. So this is kind of factorization algebra structure for mathematical reasons, kind of, for the reasons of torus localizations. So, and it's general, because you have this tori kind of basically in all reasonable stacks which you can imagine. Yeah, so then there is probably some structure which is a factorization algebra structure, which should be behind of these VOAs. Yeah, it's kind of, I don't know. I invite
how do you see the factorization algebra in this sense? How can you?
Yeah, CoHA is a factorization algebra. If you kind of spell it out properly, that's some kind of bits of that can be found in our paper with Maxim of 2008, when we speak about this coherent sheaves on configuration spaces. That's basically what factorization structure does. Yeah, I invited Alyosha Latintsev. It's number 3 on your last slide. He will give a talk, I believe, in 2 weeks, and he did some computations in geometric setup, but I don't know whether it's some lattice VOA or it's more than
yes, basically, the point I wanted to stress here is that, well, his constructions works for hereditary categories. So one can consider quiver representations or sheaves over a curve. Exactly. Yes. So in the case of in the case of quiver representations and symmetric, if our quiver is symmetric, then, well, his structure is actually not a vertex algebra structure, but, well, it's a structure, it's a quantum vertex algebra structure. So you don't have locality, it's more complicated.
Yeah.
Anyway.
You have locality, but for the shifted diagonals, you have letter Q. Yeah, this symmetricity, it's a very, very special case when your Euler form of your category is symmetric, but for the curve, it is not.
Yes,
for curves, it is not. For CP1, you have like for P1, you have Kronecker quiver and
So
so on.
yeah, in that case, you have the diagonal kind of taking that as a graph, as a graph of the braiding. So
Yeah, but what Sergey said that you have a symmetric monoidal category. In this case, you will not have symmetric. It will be braided monoidal, probably. I don't
that's
know.
right. The braiding will curve the diagonal, you know.
Shifted. What
Shifted.
what he says, if I understand, if it's quantum, then there should be letter Q. And so then your locality, it's not like Z minus W in some power kills the commutator. It's like Z minus Q in some power, actually arbitrary power of Q, like Z minus Q squared W kills something which actually, I'm not sure it's a commutator, maybe it's
Well, the X and the Z and the W won't be commuting when they commute.
No, Z and W will be commuting. No. But your diagonal, it's not an ordinary vertex. You know, that's different between, like, you know, in quantum mechanics, you have some discrete, you have the minimal length. In quantum vertex algebras, I don't know who was the first, probably it goes back to Frenkel and Reshetikhin, 91 in examples. Yeah, your minimal step is this Q, some extra complex number. And you cannot make your points closer than this Q, which means Z cannot be equal W, can be equal QW, Q squared W. You have this, yeah. So I don't know whether the axioms have been, I mean, I have not followed. But anyway, it's not a vertex algebra, but it's, well, it's quantum version, whatever. But yeah, of course. And I do not, yeah, actually it's a bit strange because with Rabchak and others, we had a non-commutative CoHA, but we did recover ordinary vertex algebra. So yeah, I'm a bit confused, not quantum. Yeah, but nevertheless, the structure kind of, I do not see it. I still do not see it after this talk.
Yeah,
I don't remember.
Well, I don't know, maybe you already mentioned it, but in the case of symmetric quivers, this quantum vertex algebra just becomes the usual vertex algebra in the corresponding monoidal, symmetric monoidal category.
I agree. Okay. Actually, yeah, it's a good point. For general toric Calabi-Yau's threefold, we do not, we cannot make a dimensional reduction of CoHA and reduce it to 2 dimensions. But for C cube, for 3-dimensional complex vector space, and that was our main example with Rabchak, found yeah, in that case, it was C cube, and indeed it's a product of C squared, just with single 2-dimension. Yeah, okay, it can explain why we see an ordinary.
Yeah, but even for brain tilings, you can still get some non-symmetric quivers with potential.
You see, unfortunately, Prochaska has left, and he wrote a paper which basically says that if you have, well, what you call brain tiling and what physicists call toric Calabi-Yau, it's glued. You see the toric diagram, it's a planar graph which is glued from very simple this Mercedes signs, which they call topological vertex in different situations, yeah, like 1 vertex and 3 legs. And we know what to assign to this topological vertex. That's what we did with Rabchak and others. And Prochaska pure algebraically proposed a construction following Fegin, actually, some older ideas of Fegin, how to glue these vertex algebras together. So then having an arbitrary toric Calabi-Yau threefold and having our result with Rabchak and others, which is basically W algebra associated with the topology, you can glue something more complicated. And in this way, you do not see a three-dimensional story. But you can ask a question, and I believe we asked that. Maybe it's a conjecture in our paper with Rabchak and others, that if you construct from the brain tiling quiver with a potential, and then you construct CoHA for this quiver with a potential, and then there should be some kind of a construction of vertex operator algebra which agrees with this conformal gluing of Prochaska. Maybe it was Prochaska and Rabchak, I don't remember. So then, yeah, I agree that it's essentially you can reduce everything to 2 dimensions, which means that to usual vertex operator algebras, yeah. But yeah. But Yamazaki actually, he constructs something with co-authors without CoHA, just by explicit formulas. For me, it looks like some quantum vertex algebras. I don't know.
Well, I suppose the formulas in your paper and in Yamazaki's are actually very closely related. I mean, on the combinatorial
they
level.
just agree. For simplicity, let's assume that it's the same. Yeah, yeah. Probably then. Yeah. Probably then. The question is how to get Yamazaki's formulas from CoHA from the quiver with potential associated to the brain tiling. And actually, I believe you can do that because you have few papers on that. Yeah. It's kind of, it's not most general explanation, but at least it's one step beyond lattice vertex algebras. Because this, I forgot how Fegin called it, conformal extension. I believe it's an algebraic procedure. It can be applied to the setup which you mentioned when you kind of described axiomatically this conformal, this C conformal vertex algebra and so on.
Or you can also do poset construction inside from the lattice view. You can get lots of other views.
Yes, but yes, you are right. Yes, you are right. But you see, if you have some, like, let me give an analogy. If you have an associative algebra, of course, you can present it as a quotient of a free algebra, but it's not always the best way. Yes, sometimes yes, but these CoHA, they appear quite often geometrically. And so then it's better to have more direct construction, at least maybe conjectural construction.
Yeah, I don't know if it in any way related. So another topic that one has here is, well, remember these locality relations, they are actually quadratic, and therefore one can apply causality.
Yes.
Well, construct causal dual and discuss all things related to this.
You had something about causal duality.
Well, I
slides, so maybe in your paper, I don't remember.
No, actually, I suppose, yeah. So basically,
Okay.
I suppose I sent you an older version without the last slide. So what happens is that right. So we have our coefficient algebra L, and it has a decomposition L plus L minus. Now we know that L minus can be is isomorphic to C, but this algebra is actually, I mean, the description even as a vector space of this part is very complicated. On the other hand, the description of L plus is simple because it is just, well, we consider these quadratic relations for L, but we just restrict it to quadratic relations for L.
I see.
Plus,
your part 3 tells that the generating series for this complicated L minus can be computed in terms of L plus, well, dual.
Well, it's very strange. L plus is relatively simple. L minus is relatively complicated. However, for L minus, we know the Poincare series because they are automatically related to H. So it's sort of another way around. We know it for L minus, but it turns out that we can also find it for L plus, which looks sort of simpler, but actually to compute its Poincare series it's more difficult. Yeah, but what is interesting is that, well, in this other paper by Dotsenko, Feigen, and Reinecke, they actually computed the Kochel dual of L plus. And now this formula indicates that actually this Kochel dual is probably the Kochel algebra. So UL plus or AQ are Kochel algebras because, well, this is sort of a numerical Kochelness. Again, I'm not sure if it has any implications for CoHAs, but this is also part of the story.
That's interesting. But is it again for symmetric Q?
Yeah, just for symmetric quivers.
Because somehow it's a bit, like this identity 5 is certainly true for symmetric and Grassmann. I mean, this kind of things, but there are some.
Yeah, I mean, it doesn't prove Kochelness. That's true, but it indicates that it could be Kochel.
Yeah. Okay. Yeah, it's interesting. All right, more questions?
I do have a question I've been reading. So earlier you said that G, you regard G as a G plus, G prime will add the one variable X. So
yes.
in this later part, what is the, and you also said that G is abating, right?
Yes.
So here, can I see where in the latter part, so what the G?
Well, it doesn't appear in our situation. So basically, so the result of Efimov is that H is U of G prime X. What we prove is more like this H dual is U of C. And C, there is a free action of the derivation on C, and therefore, well, G prime, or more precisely, the dual of G prime should correspond to C modulo DC.
I see. But this time it becomes abating the algebra, right?
C by DC. Yeah, but yeah, G prime, it doesn't have any additional structure except just a vector space. Well, G prime is an abelian Lie algebra. Here, C by DC has a Lie algebra structure, but we don't know what should be its interpretation.
Yeah, so somehow this vertex algebra structure, it's not clear why it is relevant to DT. Like in our original kind of expectations of Maxim, it was not for the dual, but for H itself. And so the kind of the dictionary was more or less clear that it looks as so quantum, but universal enveloping algebra of something. And DT invariants, they're just dimensions of this graded component. That's it. DT invariants themselves, kind of physicists computed them without algebra structure. This BPS algebra, it's kind of, it was not used in physics. I'm not sure that it is used in physics for any purpose except of theoretic device. So they did not compute the algebra structure. So that's why I asked about the vertex algebras, which certainly they do appear in physics for a reason. And so, but these DT invariants, they kind of morally, in terms of very general from the space, they appear, the interpretation of DT invariants in terms of H in G prime is similar to interpretation of H dual and C. So it just dimensions of some artificially constructed spaces. The algebra structure or coalgebra or bialgebra structure was used just in order to construct these auxiliary spaces. But DT invariants themselves, they don't know about this. I mean, they don't care about this algebra or coalgebra structure. So that's strange. That's strange. So anyway, more questions? So last chance. Well, if there are no questions, so let's thank Sergey for interesting talk. So actually we start kind of, I am afraid that February will be the month of Vertex algebras and the M seminar. Next week, Gukov will give M seminar lecture series, and there will be Vertex algebras in his talk as well. Then Alyosha Latintsev and Galachov also will has promised to give a talk, and I believe it will be in February. So you should, I mean, for graduate students, you should really learn what is a vertex algebra, at least at the level of Wikipedia. All right. So
probably we should prepare graduate students for these talks.
Yeah, but since we don't know in advance what is the background material which the speaker assumes, so then you should be prepared for anything. As Gelfand in his seminar, he once said, well, this is a very elementary talk. It assumes only the knowledge of the vector spaces and derived categories. So this is more or less what... Okay. All right. So thank you. And this is it for today. Thanks.
My pleasure.